Hi folks, welcome back to Physics with Captain Rod. The topic of today's video, charge distributions and how they're handled as far as determining electric fields. So for starters, I'll talk a little bit about just what this stuff means here. So imagine we've got some sort of group of charges, plus, plus, plus like this, along some sort of path. Now for starters, in this video, I'm going to represent that charge distribution as a red line like this. So this red path here is representing this charge distribution. Now, everything that I'm going to talk about applies to both positive and negative charges. The only thing that differs between plus and minus are the electric field directions. So for now, I'm just going to assume all positive charges. So there's three types of charge distributions to consider. You've got what are called linear charge distributions, as denoted by this little path here. Then you have, charge possibly spread out over some sort of area. So I represented that. Imagine some sort of area here. So these are all positive charges. An important thing to realize, though, is that this is two-dimensional. So it's like charge on a sheet of paper or something. And then you have what are called, three-dimensional charge distributions, and that's what this picture represents. So imagine this object here, and again, you see I tried to show that it has some sort of depth to it, with charge spread out throughout its volume. Now, for each of these charges, we can define what's called the charge density. For linear charge distributions, we would typically use what's called a linear charge density. It's usually denoted with the Greek letter lambda in about every book I've ever seen. And here's how this thing is defined. It's defined as charge per unit length. So your linear charge density would have units of coulombs per meter. Okay. Over here, in this example, our charge is spread out over an area. So here we would typically use what's called an area charge density. It's usually denoted with this Greek letter sigma. And this thing is defined as charge per unit area. So this will have units of coulombs per square meter. And then when your charge is spread out throughout a volume, we would define what's called the volume charge density. A lot of books I see use the Greek letter rho to represent volume charge densities, where this thing is defined as charge per unit volume, so it would have units of coulombs per cubic meter. Now, the idea is, what do we use these for? Well, they're used for several different things, but the main idea here to try to find electric fields due to direct computation, what we do is, I'm going to take these and move them. Let me talk about this guy first. So here we have some sort of linear charge distribution. If I pick a point in space like right here, and I want to know the electric field at that point, well, there's multiple ways to go ahead and try to do that. One of them is to try to compute it by the point charge formula. Remember that the electric field due to a point charge is kq over r squared. So we can apply this anytime we have a point charge, or at least something that's approximately a point charge. Now, if I'm sitting right here and I'm looking at this charge, this thing's not a point charge. So this formula, as it sits, does not apply. What we can do, however, is break up this charge distribution into little pieces. So here's kind of a little piece right here. Oops, maybe right here. And the idea is that this little piece right there, that is a point charge. The electric field due to this little piece points dead away. That might point something like this. Now, if I imagine this thing infinitely small, or then the electric field vector would actually be infinitely small. Let me not do that for this. Let's just imagine this small. And then this is going to be some electric field, which again is not infinitely small, just small. This electric field is going to equal K times the charge on this chunk. And what I'm going to do here is put a little I on it, where the Q sub I now is representing the charge on the ith piece anywhere along this path, over r squared, where the r in this example would be that distance. Now, the q sub I, the charge anywhere along this path, can be determined if I know the charge density at that location, which is what I called the lambda, times the length of this element here. So I'm just going to put I'm just going to put a delta S here for change in length. If you take charge per unit length and you multiply by some small length, you now have a charge. So this delta S is representing the length of that charge in this example. And then what we would do to get the electric field is we would have to sum them up. So the net electric field is going to be the sum of all of these terms, k q sub I over r squared. Now when I say sum, it's important to note here though that this is a vector sum. And again, I'll make videos demonstrating how this is done. Basically, this is done by components. This is just meant to be kind of a conceptual video. I'm not going to go through any examples, but let's talk about down here now. If I pick a point in space, maybe right here, and I imagine breaking this charge up into little pieces. So here's a little chunk. And again, the idea is I can't treat this great big deal like a point charge, but if I break it into little pieces, like this little piece, I can consider it a point charge. The electric field here, due to that chunk, points dead away. And again, that electric field is going to equal K times the charge of that chunk, so I would put an I on it to denote that, over r squared. R in this example would be this distance. And as far as where would I get the Q sub I? Well, if I take the charge per unit area, that's what this thing called sigma is, and I multiply by the area of the chunk, I'm going to call that just some sort of delta A for change in area. This will now give me the charge on that chunk. Then the total electric field we get by summing these all up vectorially. And again, I'll make a video demonstrating what I mean by vectorially. And then same thing here. If I pick a point in space and I want the electric field of this charge distribution, again, this thing right here is not a point charge, but the idea is, can I break it up into pieces that are point charges? And then if I focus on this piece, the electric field is to the right, equal to, again, k q sub I over r squared, where in this example, this would be the r. The q sub I would be given from the charge density. If I take the charge density of this object and I multiply by the volume of that chunk, I'm going to go ahead and call that a change in volume here, I would now have a number with units of coulombs. And then the total electric field we get by summing these all up. And again, this is a vector sum. I'm going to avoid that in the video for now. I just wanted this to be kind of a conceptual video talking about, what these charge densities are, and just give you an idea for why we need them or why we want them. And here's one reason why. The idea in all three cases is to break each charge distribution into pieces. Here, this piece is a linear type of piece. Here, it's an area type of piece. And here, it's a volume type of piece. You can then apply the point charge rule and write an equation for the electric fields. You do that vectorially, though. Again, I'll give an example of what that looks like here after this video. And the charge densities will come in here, here, and here when you're trying to determine the charge on your little elements, here, here, and here. So again, here's what the charge densities are. You've got charge per unit length, lambda, charge per unit area, which is sigma, and charge per unit volume, rho. And here are examples of what they're used for. I hope this video helps describe what those charge densities for and at least give you a flavor of why we would want them. Have a great day.